neutral currents at 3 level, and this is almost a very popular model, the 2 Higgs doublet model. So let me explain it. And see why it has flame for changing neutral currents and of what type. 2HDM is the jargon for 2 Higgs doublet model. So everything is almost as defined in the standard model, SU3 cross SU2 cross U1, broken spontaneously into SU3 cross U1, the same fermion content. The only difference is that now we have 2 doublets, 1, 2, plus half, I equals 1, 2, okay? And so there are differences in the Higgs potential, okay? There are many terms now with most of these. What I'm interested more is in the Yukawa, and the Yukawa is a bit similar to what we had, Y, U, K, I, J, Q left bar, phi k and u right, it's phi tilde k, plus y dij q left bar phi k, sorry, here there is an extra index k for which of the 2 Higgs doublet it is, so this k is here, ij q left I phi k d right j plus y l k I j, L left bar I phi k E right j plus Hermitian conjugate. So the difference from before is that now there are 2 Yukawa matrices for each sector. And as long as we work in a general 2 Higgs doublet model, which is what I'll do in these 5 minutes, there are 2 well-defined bases to work. So so these 2 transform in the same way. Any combination of them is also a legitimate 2 Higgs doublet representation. So one very convenient basis is often called the Higgs basis. It's a basis, okay, so I move from phi 1 and phi 2 to something that I call phi m and phi a, which are combinations of these. And they are defined, so in general, both phi 1 and phi 2 carry a vacuum expectation value, okay? So I can look at the plane of the 2 vacuum expectation value. They define a direction of the common vacuum expectation value, okay? So instead of, let's say this is phi 1, phi 2, and phi 1, or whatever, and here I have a vev, and here I have a vev. So I can now move to a basis like this, where the common vacuum expectation value is carried by one of them, and I call it phi m, and the other doesn't have a vacuum expectation value. I can always do such a transformation. Okay, so this is defined by phi a vacuum expectation value equals 0, and phi m vacuum expectation is the same v over square root of 2 as that of the standard model. I can always move to such a basis in a 2 Higgs doublet model. And if you now move to this basis, okay, so now I still have 2 Yukawa matrices. One I would call, let's say, the YMU, YMD, YML. The Yukawa matrices of phi m. Then this is now the only source of the masses. So I know what Ym is. Ymf is mfv, over v over square root of 2, because this is the source of the masses. Right? The other one does not contribute because it has 0 vacuum expectation value. So in this basis, one of the Yukawas is known. Okay, I see enough people say this. While the other one, the Yukawa matrix of the other Higgs doublet is completely arbitrary. We don't have any idea. Okay, in the standard model, there is one Yukawa, and if we know the masses, we know it in the mass basis. Here we have one that we know, the one in the direction of the vev. because that's the source of the masses, and the other, which is completely arbitrary. Now, the point is that there is another basis, and that's the basis. So in a 2x doublet model, a priori, there are 8 real scalar degrees of freedom. 3 are, as before, the would-be Goldstone boson that are eaten by the W plus, W minus, and the Z to become massive, and there are 5 others. And, okay, if we ignore CP violation, then these 5 either are a light neutral Higgs, a heavy CP even neutral Higgs, a CP odd neutral Higgs, and a pair of charged scalars. And we usually identify, so there are 2 CP even neutral, these 2, and we call the lighter one little h and the heavy one capital H, and we usually identify the one that we have discovered with this one for good reasons that I will now not go around. And what we are measuring when we are looking at the Higgs coupling is this Yukawa. And this Yukawa is, in general, neither Ym nor Ya, some combination of these. And so this H and H define another basis of 2 Higgs doublet, phi H, phi H, the doublet that contain the 2 mass eigenstates. These are the mass eigenstates. The doublet that contain the 2 mass eigenstates, little h and capital H. And the rotation between the phi M, phi A, phi M basis, where one carries a wave and the other doesn't, and the phi little h, phi large h, where they contain the mass eigenstates of the 2 CP even neutral Higgs, is called in the jargon alpha minus beta. There is a reason why it's 2, because one usually starts with the basis phi 1, phi 2, and the rotation to the phi A, phi M basis is called beta, and the rotation from phi 1, phi 2 to this basis is called alpha, and so the rotation between these 2 is alpha minus beta. And what YHF is sinus alpha minus beta YMF plus cosine alpha minus beta YAF. And so there is a part which is proportional to the masses and therefore also diagonal in the mass basis. And it has a different overall coefficient than in the standard model. In the standard model, this is 1. Here it's sinus alpha minus beta, whatever it is. But there is also another added part, which is completely arbitrary, unknown what it is, its structure, could be off diagonal. The diagonal terms are not proportional to the masses. A priori, it could be anything. And so in a 2x doublet model, in a generic one, the light Higgs has off-diagonal couplings. Its couplings to the diagonal couplings are not proportional to the masses, etc. And many things are different from the standard model. So this is an example of another ingredient that I said. If there is no single source of the fermion masses, which is a single Higgs, in this case there are 2 Higgses which are the source, then the diagonality is violated in general. Okay, so that's a second example. Perhaps I will use this model later to demonstrate other things, but this and the model that I had with U, D, and S, or particularly a model with vector-like quarks, show that things are really special of the standard model, that there are no flavor-changing neutron currents at 3 level. So that's the 5 minutes exercise, and I'll do another 5 minutes exercise. Yeah. So the next thing, which is 5 minutes, is, for me, I think it's funny that it's 5 minutes, because I'm going to explain in 5 minutes a work that completely, I will prove it, a whole exercise that won a Nobel Prize. I think to be able to explain the physics of a Nobel Prize in 5 minutes in a way that you hopefully understand is, okay, it's kind of entertaining at least, if nothing else. So I will talk a little bit about CP violation. And I will prove in a minute. It will allow me to repeat the exercise once more of counting how many physical parameters there are starting from the Yukawas. I will do it for 2 generations and see the difference from 3 generations. Before that, let me tell that I'll talk within the remaining hour and a half that I have also quite a lot about CP violation. So there are 2 reasons to be interested in CP violation. One is the cosmological puzzle that I mentioned, the fact that CP violation of the standard model fails to explain the baryon asymmetry of the universe by many, many orders of magnitude. And the other, which is often overlooked, is that CP is a good symmetry of strong interactions. And that's a huge advantage in calculations. So if you ask a responsible physicist, an honest one, to calculate the decay rate of B going to psi k short, if he's honest, he'll tell you, I can give you an order of magnitude at best. That's it. Nothing better than that. If you ask him to calculate the CP asymmetry in the same process, B to psi k short, he and I can do it to a few per mil accuracy. So this difference, we don't know the rate, but we know this CP asymmetry is B to psi k short minus the rate of B bar to psi k short over their sum. That each of these we know to within order of magnitude, but that this combination we can calculate to an accuracy of a few per mil is something fantastic in probing and testing the model, and that's advantage of CP violation. So yeah, Silvia is here. So I'll do I guess we'll let Silvia talk and I'll do the 2-generation exercise after lunch break. Yes? Good.
Mi dispiace moltissimo. È un disastro. C'è già. Okay, good morning. Sorry for the delay. The microphone, yes. Okay, I hope this works. Okay, so yesterday we talked about neutrino oscillations and I explained why that is so important, as it explains or tells us that the neutrinos have mass and mix. So what are we going to do today? In this lecture, we're going to look at neutrino masses, how can I extend the standard model with a mass term, how I can then explain these masses from physics beyond the standard model. And also how we can measure them. It's hard, as I will show you, but there are some experimental ways in which we can try to pin down the values of the masses. So far, as I already discussed yesterday, we only know mass square differences. And in this afternoon lecture, instead, we look at the problem of mixing and the neutrinos in cosmology. So what I'm going to discuss today, first of all, is what we know about neutrino parameters. At the end of the lecture yesterday, I gave a few slides where kind of to set what is the current scene of neutrino experiments, and then what do they tell us? This is the first thing we are going to look at today. And then so what are the questions that are left to answer from a phenomenological perspective in the field. So today we focus on those related to neutrino masses. So first of all, the nature of neutrinos. In my opinion, that is probably the most important question we have in neutrino physics, because that establishes if lepton number is violated or not, and tells us then what type of masses neutrinos can have, so how I have to extend the standard model in order to explain them. So we look at how to test the nature of neutrinos. You have to look at the processes which violate lepton number. The most sensitive is neutrinoless double beta decay, even if there are other ways that I will actually not discuss because they are much less sensitive than that. And then we will go and look at what type of neutrino masses can have. Probably has already been discussed by Yossi in his lectures. So Dirac masses and Majorana masses. And so once we add them to the standard model, then we have to try to explain how they come about, like for the charged leptons or for the quarks, you have a Dirac mass term, and you know that this comes from the coupling to the Higgs boson. Okay, so this is not working. Because it's not connected, there's no way to connect my laptop, no, to this. Well, okay, it doesn't matter. I can change it just like that. Okay, so this is what we know currently about neutrino parameters. So we have two mass square differences. So this is delta m square 3, 2, which is the one which matters in atmospheric neutrino oscillations. As I mentioned already yesterday, and we are going to look in a minute, we don't really know the ordering. So we don't know if M1 is bigger or not than M3. Just to clarify, the ordering is somewhat arbitrary. I could choose to have always the lightest one and call it M1. But this would mean that we need to change the meaning of the mixing angle compared to what we observe. So what is the kind of, in the literature right now, basically everybody prefers to stick to the meaning of the mixing angle. So for example, theta 1,3 is always the mixing angle which enters in the reactor experiments. And by fixing the meaning of the mixing angles, then you have to kind of change the ordering of the masses. So you could have its lightest mass either M1 or M3, depending on the neutrino mass ordering. So this is the one we don't know the sign of, and is around 2.5 10 to the minus 3 eV squared. So I mean, small, but I mean, the largest of the two. And this is the mixing angle associated again to atmospheric neutrino oscillation and accelerator neutrino oscillations, theta 2,3. And this, you see, could even be maximal. In any case, it's very large. It's very close to 45 degrees. That is why when we are thinking about where does the mixing come from, a very likely interpretation is that maybe there is a symmetry at work. And this is what tells me, okay, this is what tells me that maybe there is a symmetry at play, at least in my opinion. Then we have we have delta m squared to 1. This is the solar mass square difference. Notice that this is positive. We know that because if you remember yesterday, the resonant condition, that depends on the sign of delta m square. If you remember yesterday, we said that for having a resonance, you need to have that delta m square divided by 2e cos 2 theta needs to be equal to square root of 2, etc., etc. So this is possible in the neutrinos only if delta m squared positive. Otherwise, you will have it in the anti-neutrino sector. But solar neutrinos are electron neutrinos. Notice also, somebody yesterday came to discuss with me this after the end of the lecture. Obviously, this depends also on the sign of cos 2 theta. But again, by convention, I mean, we choose to have the value of the angle between 0 and pi over 2, which then means that the cosine is positive, which also means that then delta m square is positive as well. It's the simplest choice we can possibly make. It's a choice, though. And this comes with the mixing angle in the solar sector, which is theta 1, 2. Is large, around 0.3. Not maximal, actually significantly not maximal. I will show you that this is important in neutrinoless double beta decay, but still is a large number. This is maybe less relevant in pointing towards a symmetry, but again, many models with symmetries can actually explain also this angle. And finally, we have the third mixing angle, which is theta 1, 3, which is the smallest one, but as you can see, is not particularly small, it's around 8, 9 degrees. And I'll come back to this. We start having some hints in favor of CP violation. I mean, these contours means 1 sigma, 2 sigma, 3 sigma, etc., 90%, 95%, etc. So again, take away one thing only from this lecture, then take away this, that we now know that neutrinos have masses and mixing, and taking the standard model to be just the one which includes left-handed neutrinos only, and that's it, this means physics beyond the standard model. So let's look at the neutrino masses. The fact that you have two different mass square differences means that we need to have at least 3 neutrinos. 3 massive neutrinos is good because we have 3 flavor neutrinos, so you expect to have 3 massive neutrinos at the least. We can have more if we have sterile neutrinos, so neutrinos which don't have interactions but can still mix. And these are the 2 ways in which you can order them. So you have 1, 2, 3 here, and 1, 2, 3. So you see that delta m square 3, 1 is positive in this case and negative in this case. These colored bands correspond to the fraction of nu e, nu mu, and nu tau. As you see, this is fixed, is the same. So 1 has always the same component. This is what I meant with I fix the meaning of the mixing angle. I mean, the composition of each mass in terms of the neutrino flavors is the same. This forces me to rearrange the masses in this way. And this change is due when I change the delta phase from 0 to pi. Is a kind of brings in this uncertainty in the composition of the 3 massive states. Now, once I fix the ordering, normal ordering or inverted ordering, let me say also one thing. In the literature, you find also hierarchy. I don't personally like to call it normal or inverted hierarchy because we don't know if neutrinos are hierarchical. Indeed, they could be even quasi-degenerate, even if there's a bit of tension now with cosmology for that. But they could also have a kind of a relatively mild hierarchy. So I prefer to call it ordering, which doesn't kind of imply any prejudice about the values of the masses. So once I fix the ordering, then I can express each mass in terms of just one parameter. And let's take the smallest mass. In this case is M1. So I can write M2 as the square root of M2 squared, obviously. Then I can subtract and add an M1 squared. And then this is the delta M squared to 1, which I have measured in, delta M squared to 1, that I measured in solar neutrino experiments. So this I know, and Camland in particular. So this I know. And this is the known parameter, M1, which kind of sets the scale of the neutrinos. And I can do the same thing for M3. As given here. In the inverted ordering, I can do the similar thing. Notice that in this case, M1 should be a 2 here, sorry. So M1 and M2 are quite close in mass with just a difference brought in by delta M squared to 1, so roughly a few percent difference. So if I want to know neutrino masses, which is information I want from a theoretical perspective to try to explain them, I need to have the values of M1, M2, and M3. So I need to know the ordering and the scale. And so various experiments can give us information on some of these, either on the ordering or on the scale or both combined. So this is the current picture. So what is left to know? But first of all, the nature of neutrinos, whether they are Majorana or Dirac particles. I mean, in the standard model, they are the only neutral fermions we have, so they are only ones which can have a Majorana mass term, the only ones which can be of Majorana nature. So this kind of makes them a little bit special in this respect. And for me, this really is fundamental because it's related to the lepton symmetry. And so it tells really what is kind of the properties of the overall theory we have in nature. Is it lepton number conserving or not? Then we need to know the values of the masses. I already mentioned the absolute scale and the ordering. We need to know if there is CP violation in the leptonic sector. Maybe this can give us some insight on why CP is violated. And then we want to know the precise values of the mixing angles. I'll come to that tomorrow because this is information which is very important to try to understand where the mixing comes from. So what is the flavor structure? Typically, flavor models or any model that you may like has predictions for the values of the oscillation parameters, particularly the mixing angles and the phase, many times relations between them. And so you can try to test them if you know precisely enough the values of the mixing parameters. Something that I'm not going to cover at all in the lecture is if the overall three-neutrino mixing picture is correct or not. We already discussed yesterday in some of the questions. There are some hints in favor of sterile neutrinos. So there is, maybe let me spend just a couple of minutes on this. There is the LSND experiment, which look for anti-nu mu into anti-nu e appearance, and they found some excess of events seeming to indicate an oscillation of anti-nu mu's into anti-nu e's. Now, this happens at very short baselines. You remember, the oscillation probability depends on delta m square. So if you go to very short baselines, you need a large delta m square to have a sizable oscillation. So that means a delta m square around EV squared. And so this cannot be accommodated with just 3 neutrinos, because then you have 3 delta m squares, and you have 3 delta m squares, you need to have 4 neutrinos. From the invisible Z decay, you know that there are only 3 active neutrinos, so the 4th one cannot have standard model interactions, is a sterile neutrino, so-called. And so you will end up with nu E, nu mu, nu tau, and this nu S. You will have a 4x4 mixing matrix, and then you will have 4 massive states, nu 1, nu 2, nu 3, and nu 4. And this also allows me to clarify one thing. People talk about sterile neutrinos, meaning sometimes a nu S and sometimes nu 4. Now, nu 4 has a standard model interactions because it mixes a little bit with the active ones, and so in that way it can couple to the W and the Z. So if you're talking about nu 4, this is nearly sterile. If you're talking about nu S, this is the flavor state, the one which doesn't have any standard model interactions. So there is LSND, then there is reactor neutrinos. So there is their experiments which look for anti-nu E disappearance, as I already mentioned yesterday. And some of them have looked at disappearance at very, very close distances of a few tens of meters. And they found that with respect to the computed fluxes of neutrinos, there are less. Now, that's an issue because, first of all, it would indicate again a delta m square in the same range, but at the same time you are relying on a computation of the neutrino flux, which is very difficult, so that is where the uncertainty comes from. Then there is mini-boom. So mini-boom was constructed to test the LSND results. It came out with its own anomaly. So there is an excess of nu mu into nu E events, so nu E events at low energies. So the shape is really that it picks up as you go towards 200 MeV. So again, people have fitted the whole thing together. If you want, you can force this excess to be explained in terms of neutrino oscillations. The problem is that any of these appearance experiments, so when you're looking for an appearance experiment, for example, nu mu into nu E, you need both the mixing of mu with the 4th neutrino and E with the 4th neutrino. So the probability actually is proportional to this product, and then you have the sign square with the mass, etc. Disappearance experiments instead look at separately, if it is a new mu disappearance, looks at this term here. If it is new E disappearance, like the reactor experiments, is this term. There are, in particular, experiments like CDHS and atmospheric neutrinos that constrain this term to be quite small. Reactor neutrinos want this term to be not too large, and when you put them together, it's difficult to get enough of this product that can explain the oscillation. So there is tension in the data. I mean, some people like it as an explanation, so can somehow force the explanation anyway on the data, and they might be right. Some people think that this tension disfavors this interpretation in terms of neutrino oscillations. Personally, I mean, it could be either way. What personally I don't particularly like is the shape of the events, of the spectrum of events in mini-Boon. To me, it suggests something else. Either is some nuclear effects which have not been properly taken into account, or some new physics which gives kind of not an oscillation type shape to the signal. But okay, this we go into kind of a tangential direction to where I want to discuss. What is important is if in any experiment, because now we have microboon, which will release data at some point soon. Then there is the SBN program at Fermilab with 2 other detectors, Icarus and near detector 1 SBN. So there is lots happening and many other experiments as well. So they might find that some of these anomalies, or all of them, or just some of them, are indeed correct, and there is some new physics there. If this happens, basically you have to take 50% of my lecture and change it, because now we have to think about not anymore kind of flavor models for 3 neutrinos. We have to think of giving massing also to the sterile neutrinos. Why are they light? Why the mixing is, whatever it will be measured, etc., etc. So if anything is confirmed regarding beyond the standard picture, then it becomes a completely different theoretical ballpark and becomes extremely interesting and to look at. So as I mentioned, there are lots of experiments which can address these questions. We're going to look at some of them. But let's focus today on the questions which relate to neutrino masses. So in particular, the nature of neutrinos and the measurement of neutrino masses. Let's first see how we can get the information we need from experiments. So let's talk about, actually I move to the board. Let's talk about, the nature of neutrinos. So as you know, neutrinos could be, or at least, as I already told you, Dirac or Majorana particles. Here we go. So, kind of naively, we can say that a Majorana particle is indistinguishable from its antiparticle. I mean, more precisely, we first need to introduce what is charge conjugation, that probably Yossi has already done. So this is just a recap of what you have probably already seen. Okay, so let's just summarize it. So charge conjugation. So this is a transformation which changes the quantum numbers. So if you have an electron, you will get a positron. But and so in particular, if you think in terms of annihilation operators and creation operators, this will change an A to a B in the Dirac spinor. So, and with this, we can introduce what is the charge conjugated field, which I call psi C, which is C, where this is a matrix that I define in a minute, psi bar transpose. I guess you must have seen this in the standard model lectures, right? So what are the properties of C? We have that C gamma alpha, C dagger is minus gamma alpha with a transpose here. And then we have that C dagger is the identity, and C transpose is minus C. If you choose one specific representation of the gamma matrices, for instance, the Weil representation, then, so in Weil representation, you have that C is I gamma 2 gamma 0. So one thing that I would like you, and I leave that to you as an exercise, is to show that if I take the C of a left-handed field, what I get is a right-handed field in terms of chirality. This is important for when we discuss neutrino masses. So you can do it in two ways. So this is my suggestion for an exercise. One is just choose the Weil representation. In that case, it is trivial because this gamma 2 has the off-diagonal sigma 2s, and what it does, it flips the top and bottom part of your 4 Dirac spinor. So it flips the left to the right and vice versa. But that's the easy way. I think what I suggest you to do instead is to use the properties of the C matrix and do it independently from the representation. And then you can show this property here. Now, with this, we can introduce what is a Majorana field. So Majorana field satisfies the Majorana condition. So psi is equal to its conjugate. If I think in terms of the chiral components, psi needs to be psi left plus psi left C. So when I take the charge conjugation, I swap these two terms. And this is its left-handed component, and this is right-handed component. If you remember what I just said, that the charge conjugation swaps A and B creation operators, immediately you realize that if I look at the second quantization for the field, this will contain, let me put that, A and A dagger. So just one type of particle, not two. So a Majorana field has only 2 degrees of freedom and not 4, like this Dirac spinor. And remember also that, now it's always useful to think of it in these terms, if you are dealing with a Dirac spinor is made of 2 Majorana particles which have the same mass but opposite CP parity. You can always kind of relate it to. So the 2 Majorana fields give you the 4 degrees of freedom. And with respect to a Dirac spinor, it has, first of all, the same propagator, but it has additional ones because I can apply the Majorana condition. Remember that this is a C psi dagger transpose. So you will have propagators of the time psi psi or psi bar. These are the ones which enter in lepton number violating processes, for example, in neutrinoless double beta decay. We'll come to that in a minute. So, as I said, in the standard model, neutrinos are the only ones which can have these properties. Now, how are we going to test if neutrinos are Dirac or Majorana particles? That is with neutrinoless double beta decay. This is by far the most sensitive process we can have. So what do we mean with this process? This is when, in a big nucleus, you have that simultaneously 2 neutrons decay into 2 protons and 2 electrons. And in between, you can have a variety of things, but from what concerns us in terms of neutrinos, at least for sure you have the exchange of 2 Ws and here a Majorana neutrino in between. So this obviously happens in a very large nucleus. So, for example, germanium 76, molybdenum 100, xenon 136, etc. So the nuclear structure is extremely complex. So if you think of the decay rate, which is what you can measure for this process, actually to the -1, this is proportional. There is a factor of proportionality which comes from the lepton sector that I know is called the phase space factor. I can compute it exactly. But what matters from our point of view is the effective Majorana mass parameter. I'll come to that in a minute. And then there's all the nuclear structure. And the hadronic part. So you have to think of the D, which goes into a U, embedded in the nucleons, which are embedded in the nucleus. So all of this hadronic part is parameterized in terms of what are called the nuclear matrix elements, which are very difficult to evaluate, and so there's still kind of an uncertainty in the exact value, and these also change very much from one nucleus to the other. So you have to compute them separately for if it is molybdenum or xenon or tellurium, you have to compute it in a kind of separately, and you can get significantly different results. What is a problem from the neutrino point of view is that, let's say that we have currently bounds, or maybe we will measure the half-life at some point. Now, once we do that, in order to extract the effective Majorana mass parameter, which is what we are interested in from a neutrino perspective, we need to know the nuclear matrix elements. And so kind of this link between the two is always kind of made difficult by the uncertainty in the nuclear matrix elements. So what is the effective Majorana mass parameter? So this M effective, well, we can look at its properties from here. So first of all, in this propagator, we have to think of, this is a new E, so we need to expand it in terms of the massive components. So we will have to expand this new E in terms of the new I's, so UEI, new I, and then sum over these are three propagators. You will have an UEI here and an UEI here. But this is of the type of propagators which are not available for Dirac particles. This is a propagator which brings in an UEI squared term, not modulus squared, but just squared, because you have a kind of Majorana type propagator here. The other thing is, in the propagator, in the numerator, remember, you have a P/ and an M part. Now, you immediately know that this must depend on the mass, because if I send the parameter which controls the breaking of a lepton number to 0, this process must go to 0, so the decay rate must go to 0. And so, what is the only parameter that I have in this theory which breaks lepton number is the mass. So you can do it formally. You can look at the gamma structure that you have here, and you will see that the P/ terms kind of doesn't contribute. But you can just guess it from the symmetry properties of this process. So basically, this is the, and we sum over I. This is the effective Majorana mass parameter. You remember, the typical momentum exchange is around 100 MeV. The masses are sub-eV, so in the denominator, you can neglect the mass squared term compared to the P squared term. So this gives you kind of the dependence on neutrino masses. So when we talk about neutrinoless double beta decay, from a neutrino perspective, this is the only thing we care about, this expression. Now, we know quite a lot about neutrino masses and mixing, so we can go and compute M effective for the various neutrino mass spectra cases, and then we can compare that with experimental bounds or sensitivities. So let's do that. Let's start first. So let's look at the predictions for M effective. So the first case we consider is the normal hierarchical spectrum, which means that we have normal ordering plus the fact that the smallest mass is negligible. So if we do this, then we know what the M1 and 2 are. So M1 is negligible. M2, from that expression we had before, is the square root of delta M squared to 1. So we know how much it is, roughly 0.01 eV. And then we have M3. Let me forget about the delta M squared to 1. Is simply related to the delta M squared atmospheric. So we know that this is roughly 0.05 eV. And as I said, this is roughly slightly smaller than 0.01 eV. And so we can plug that in the expression. So if I look at M effective in the normal hierarchical spectrum, I get, so the first M1 term is negligible. Then I have UE2 squared. If you go back to the parameterization of the PMNS matrix that I gave yesterday, this is cos square of theta 1, 2. And then we have, okay, there's also a cos square theta 1, 3. Doesn't matter too much. No, sorry, sine square theta 1, 3. Sine square theta 1, 3. And then we have M2, which is the square root of delta M squared to 1. Plus UE3 squared is sine square theta 1, 3. And then I have delta M square 3, 1. But I have also the phases. I'm just taking squares, not modulus squared. So I will have a phase here, but I look at the phase difference. So I will have here an e to the alpha 3, 2, actually plus 2 delta. So at most, the extremes of this phase here could be either 0 or pi. 0 gives me a plus, and pi gives me a minus. So in this way, I can look at what are the extremes of the predictions for M effective in this case. And what you get is something in the order between 1 and 5 millielectron volts. So it's extremely small. It's small because the largest mass is suppressed by the small mixing. Let me also look at the inverted hierarchical case, which corresponds to having inverted ordering plus negligible lightest mass. And in this case, we can again look at M effective. So we know that M1 and M2 are roughly given by delta M squared 3, 1. So are both roughly equal to 0.05 eV. And then I can express M effective. So I will have UE1 squared, which is cos square theta 1, 2, cos square theta 1, 3. And then I will have UE2 squared, which is sine square theta 1, 2, cos square theta 1, 3, with the relative phase in between. Let me call it alpha 2, 1. And the common mass, which is the square root of delta M square, let me put it here, atmospheric. And so actually doing just a little bit of trigonometry there, I can rewrite this as the square root of 1 minus sine square 2 theta 1, 2. Let's forget about theta 1, 3, cos square theta 1, 3, which is nearly 1, sine square alpha to 1 over 2. And then I have the square root of delta M square atmospheric. So in this case, this is definitely much bigger. Notice that when I have here the minus sign, this is cos 2 theta. Cos 2 theta is 0 if I had theta 1, 2 to be exactly maximal. That's why I said, the fact that theta 1, 2 is large but non-maximal has important implications for neutrino-less beta decay. Because what it does, it means that this term here cannot go down to 0. Actually, it's quite largish. So what you get is a prediction roughly between 10 and 50 millielectron volts. And so this is definitely larger. And then you have, we can look at the quasi-degenerate case, but I leave that to you as an exercise. In this case, the masses are much bigger than the mass square differences, and so I can take them all to be of the same order. You will get an expression which is the same as this, but with here the common mass. And anything in between. Here I went to the extremes. So here I have large delta m squares. There, instead, I have negligible lightest mass, but you can have also the intermediate regime. So if you look at the overall picture, this is what you get. So these are the full predictions for neutrinoless double beta decay. I left the charger. So this is the normal hierarchical regime, where we said it's very small, between 1 and roughly 5 millielectron volts. This is the inverted hierarchical case. So you see, in the case of inverted ordering, you have this lower bound. So if you knew that neutrinos have inverted ordering in terms of masses, then you knew that at most you can go down here. So if you had an experiment which is sensitive down to here, you would have a guaranteed result if neutrinos are Majorana particles. But we don't know the ordering. Indeed, there are some hints in favor of normal ordering, but still very controversial and weak in my opinion. So indeed, the effective mass parameter could also be in this region here, which is the region of normal ordering. And there is also this special kind of range of values of the masses for which you have an exact cancellation. So there is no guarantee that we will find it. We could have neutrinos to be Majorana particles and still never be able to find neutrino as double beta decay, if we end up being exactly in this region here. So we don't know. This is what the experimental situation is. Now, this is the bound from Gerda 2, which uses germanium. This is the bound from Camlan Z, which is the Camlan detector, but then enriched with xenon. And there are many other experiments which are kind of starting. There is Cuore here in Italy. Majorana is probably joining Gerda. We have Snow Plus, which is also starting. Super Nemo, which is, well, it's going to start in a little bit of time. But, so there is a huge amount of activity in this area. So they use different nuclei. So it's difficult really to compare the sensitivities one to the other, because as I said, their sensitivity, in order to convert it here to a prediction for M effective, I always suffer the problem of the nuclear matrix elements. That's why you don't have, so I have to do something about this. So you don't have just a number, but you have a range which takes into account the fact that these nuclear matrix elements, I mean, there are different predictions for them by different groups and using different type of nuclear theoretical models. Let's see if this helps. What is interesting is that between the current generation and in particular the upgrade of the current generation, people plan to get to roughly 15, 20 millielectron volts. So cover completely the inverted ordering case, and then we'll see if we find something or not. Now, as you see also here, as we're going to discuss how to extract information about neutrino masses, neutrino double beta decay can give you some information. For example, if we were to find a signature now, this would tell us that neutrino masses are relatively large, kind of in the border between kind of a partial degeneracy and a quasi-degeneracy. And so we would know that we are kind of up here, and we would have a lower bound on the value of neutrino masses. If they find nothing down to 10 millielectron volts, then the inverted ordering is excluded if we are talking about Majorana neutrinos. The only option would be the normal ordering. Obviously, if we were to find that and find that it is inverted ordering, then as theories we come up with nice models in which you have cancellations with beyond other physics, etc. For example, low energy CISO would be very simple. Actually, let me make a comment on this. I'm talking about only the case of 3 light neutrinos, and I'm not going to really discuss other extensions. But anything which breaks lepton number, so heavy sterile neutrinos, R parity violating supersymmetry, etc., will end up giving you a contribution to neutrinoless double beta decay. Not necessarily an important one. You have to evaluate, depending on the model, if that is important or not. There is a special case, which is the case in which I have a very low energy CISO with the new sterile neutrinos are sub 100 MeV. In this case, they contribute together to neutrino masses, light neutrino masses. So basically here you just add the mixing of with the sterile neutrinos with the mass of the sterile neutrinos. If you look at that, we'll do that when we talk about the CISO, that is exactly the MEE term in the mass matrix, and that is 0 because of SU2. So if you have a low energy CISO, you have Majorana neutrinos, but you will have 0 M effective, so you will not be able to see neutrinoless double beta decay. You have to then search for these sterile neutrinos in other ways. Yes?
So M mean is greater than 0.5?
No, this is 0.2. This is log scale, so this is roughly 0.2.
0.2, yeah?
Yeah.
So in that case, can we, the sum of neutrino mass from cosmology is 0.23. So how can we explain that?
No, okay, so if we were to observe that, then you have basically 2 choices. One is to say that there is something else happening in the neutrino sector. So you can still have very light neutrinos, so for example, normal hierarchical spectrum, and something else which gives you this contribution to neutrinoless double beta decay, for example, a light or heavy sterile neutrino. So neutrinoless double beta decay would not be dominantly mediated by the light neutrinos, which are too light, but by something else. And then you can try to look at models which do that. Or you can say there's a problem with cosmology. Now, when I extract the neutrino masses from cosmology, I assume, first of all, that I know quite well the systematic errors. It's always difficult to evaluate that. And so there's always an uncertainty which comes with that. So this 0.23, maybe it's not 0.23, maybe it's 0.4 or 0.5. The other possibility is that you don't have an experiment, right? You have only one universe. And in this one universe, you have an evolution that you try to determine from the observations, but still you assume a cosmological model. You assume that it's lambda CDM typically. So the 0.23 EV bound on the sum of the masses comes assuming lambda CDM. If I modify that, I could change this bound. I will not have much time to talk about it, but it's not so easy actually to do that because you have many different observables at different redshifts. And these kind of constraints different cosmological parameters that you have in different ways. The one which is mostly degenerate with the neutrino masses is W, so basically the model of accelerated expansion. So, for example, there has been papers in which they looked at modified gravity models, and in that case, in some of these models, you can relax the bound on neutrino masses. So instead of having 0.23 in those models is, I don't know, 0.4, 0.5, 0.6. So if we were to find neutrinoless double beta up to here, as I said, you have these 2 avenues. It would be very interesting to understand cosmologically what it tells us. As I said, it's non-trivial, though, to modify cosmology to accommodate significantly large neutrino masses.
So one thing, just like if QD spectrum is true, that means definitely there is a neutrino beyond active neutrinos. There are new neutrinos, right?
If
QD spectrum is coming as a true spectrum,
no.
Then
if you have, for
because,
instance, yeah, please.
Because 0.23 is only if I consider active neutrinos. As you told, if I include sterile neutrinos, then yeah, lambda CDM gives 0.65 or 0.55. So that's including sterile neutrino.
Yes, but you can just modify gravity, for instance. Choose a model of accelerated expansion which is not lambda CDM. With modified gravity, you might be able to do, to kind of relax the bound without including sterile neutrinos. So the question would become more compelling if you see a quasi-degenerate spectrum of relatively large masses in direct mass measurement, in particular in beta decay experiments. Because in that case, where there you have no choice. I mean, there's basically your experiment has, there's no easy or even difficult way around the bounds you get or the measurement you get. So if Catherine comes up with a positive result, unlikely but possible, then you know the neutrinos, and in particular these neutrinos, have 0.2 or above EV masses. Then really you have to think very seriously what you have to do to cosmology to make compatible with this very large, I mean, in this context, quite large masses for the neutrinos. For neutrinoless double beta decay, you have this escape that you can kind of modify the neutrino theory to accommodate it. So how do you search for neutrinoless double beta decay? Well, there is another process, which is a standard model process, which happens at the same time, which is when instead of kind of linking here with the propagator, you are actually emitting the two antineutrinos. That is the two neutrino double beta decay, which is a standard model process. It's very suppressed, obviously, because you have a GF squared. But there are certain nuclei in which the single beta decay is not allowed because the initial nucleus is heavier than the daughter one. So in that case, you cannot have single beta decay. And then you can search for double beta decay. And actually, there's been observed, for example, in calcium, in many different types of nuclei. So in those nuclei, you can also search for neutrinoless double beta decay. And here I showed you, well, this is more or less what's happening now. You have Kam-Lanzen, you can EXO 200, Gerda, Cuore. Now Cuore is starting. This was just the first hour of Cuore 0. And this is the way you look at it. So you try to reconstruct this part of the spectrum. And so typically you have lots of radioactivity, lots of things going on, which give you peaks and various signatures. This is, you're looking at the energy deposited by the two electrons in the detector. And you expect that right at the end point, you expect this little peak. So it's an extremely challenging measurement. You have to go underground. You have to control your backgrounds. I mean, the radioactivity which comes from the walls of your cavern could be a problem for this type of detectors. It's really extremely low backgrounds. And there's lots of things going on. So this is an area where we expect a lot of activity already now and in the coming years. So it's an area to watch. I'm going very slow, so let me move to the determination of neutrino masses. So maybe I'll just flash a few things, but because I want to move on to the more theoretical part about explaining neutrino masses. So if you want to measure the mass ordering, you can get some information from neutrinoless double beta decay, as I already mentioned, but the best way is to look at neutrino oscillations which either rely on matter effects. Remember, matter effects depend on the delta M square. We discussed that already yesterday. So you have either long baseline neutrino oscillation experiments like DUNE or HyperK, but HyperK is a too short baseline, so DUNE is really the one which can give you the best information, or atmospheric neutrinos, because you have neutrinos coming through the mantle and the core, so you have matter effects which are more complex than the ones I discussed yesterday. I don't have time to go into it, just to let you know that there are experiments which are looking at this. There is Pingu, although we don't know if it will get approved, Orca, Ino in India, so there is activity in this area, and HyperK itself can also provide information on this. Now, if you look at the values of the masses, you have beta decay and neutrino cosmology, in addition to neutrinoless double beta decay, which can, again, give you some information. So let's not, I don't want to discuss much of this. You have everything in the slides, so you can look at the sensitivity of the experiments, etc. Instead, let me just spend 1 minute on beta decay. This is a single beta decay. So you know that there is a spectrum of electrons that you can measure. And if neutrinos have mass, as we know, then the spectrum at the end point is shifty because the electron cannot carry away all the energy available, but it's all the energy available minus the mass of the neutrino, because that is energy carried away by the neutrino necessarily. And so by looking at this kind of change in the spectrum at the end, you can deduce introduce a bound and possibly measure the value of neutrino masses. So this is where kind of the difficulty lies. This is very difficult experiments. Kind of the bounds we have are around 2 eV, so very far from kind of the cosmologically interesting region. There is now the Catherine experiment, which is starting, and this will reach a sensitivity down to 0.2 eV. And because it's such an important piece of information, there are kind of ideas to go beyond that, and there is Project X, which it's claimed that it will reach 40 milli-electron volts. We will discuss this much more in detail tomorrow. Just here to mention that, indeed, currently, the best kind of bounds we have on neutrino masses come from cosmology. As you see, the values can be very different depending on how you measure, then, the impact of neutrinos on structure formation in particular. We'll discuss that much more in detail tomorrow, so I don't want to discuss too much of that here. Let's instead move to the more theoretical part. We know neutrino masses. Now what we want to do is, first of all, extend the standard model to include a mass term for them, and then see how these mass terms can be explained from physics beyond the standard model. And so when I talk about neutrinos, for me, they're always, I think of them as a window beyond the physics beyond the standard model. And I look at there are two aspects. One is the problem of masses, one is the problem of flavor, and in reality, the two are interconnected. For these lectures, I'll somehow split it into, we look at neutrino masses now, and the problem of flavor this afternoon. Okay, so let's go back to the board and now discuss what type of masses neutrinos can have. Well, first of all, they can have a Dirac mass like all the other fermions. Where am I? So here. For that, we need to extend the standard model by introducing a right-handed neutrino. It's not major extension. And in fact, in many, for example, gap theories or extensions, BSM, you will introduce right-handed neutrino necessarily, for example, in SO10, etc. So let's look at Dirac masses first. So in this case, I introduce a right-handed neutrino, which is a different field compared to the left-handed one, and then I can write down in my Lagrangian a Dirac mass term of this kind. I will have psi bar left, psi right, and Hermitian conjugate. Nothing special about it. Oh, let me call it neutrino, as we are dealing with neutrino. There's nothing really special about this mass term except for one thing. It preserves lepton number. So how do I see that? So under a lepton number transformation, lepton, so I have nu left goes into e to the I alpha nu left, and nu right, I can choose the same phase for nu right, and in this case, this is invariant. So lepton number is preserved. So maybe let's discuss right away how this can arise in physics BSM. Well, very simply, I can introduce a coupling to the Higgs with a coupling Y nu. I'll couple the leptonic doublet to the Higgs. I have nu right. When the Higgs gets a VEV, this will give me exactly the Dirac mass for the neutrinos. So, there are a variety of reasons why many theorists, including myself, don't particularly like this explanation of neutrino masses. But first of all, I agree with what Yossi said yesterday. This is a major change to the standard model because you are imposing the lepton symmetry. So, as you know, the lepton symmetry is an accidental symmetry in the standard model, so it happens to be there by the fermionic structure we have and the gauge interactions, but could be be violated. I mean, there's no fundamental reason why it should be preserved. In assuming neutrino masses to be Dirac, then we are imposing that to be a conserved symmetry of nature. And as Yossi mentioned, we expect global symmetries to be broken at the very least by quantum gravity effects. So there should be some kind of terms which bring in some lepton number violation, and so some Majorana mass term. The other reason, so this is kind of, I would say, the key reason. The other reason why I don't particularly like it is, first of all, let's look at the couplings you need. The coupling is the neutrino mass divided by the value of the Higgs. So this will turn out to be 10 to the minus 12, or depending on the exact value of the masses. So that is the order we're talking about. So this is a problem of fine-tuning. You know, unless I find a good reason for having such small coupling, I expect these to be, I would expect this to be 0. So again, some people might come up with models. There have been some, for example, attempts in extra-dimensional theories in which you have the sterile neutrino in the bulk, the standard model on the brain, and because of the small overlap between the two wave functions, then you explain why this coupling is so small. But there are other reasons. Now, if this is the explanation of neutrino masses, then I would expect to have a hierarchical structure for the masses, like in the quark sector and for the charged leptons, and mixings similar to what I find in the quark sector, so small mixings. Instead, here I get masses which are not very hierarchical, if none at all, and mixings which are large. This, to me, suggests that there is some other explanation for neutrino masses, and the simplest thing I can possibly do is look at that dimension 5 operator that Yossi mentioned yesterday. So this can kind of, so let's then move on to Majorana masses, which as kind of I personally prefer. As I said, keep in mind this is prejudice. We might end up knowing that neutrinos are Dirac particles, or at least in some cases, we could draw this conclusion, assuming that there's no other relevant physics in neutrinoless dbeta decay. But so let's look at Majorana masses. So, as I already told you earlier, if I look at the charge conjugate of a left-handed field, this is right-handed. So instead of using a different new right to write the mass term, I can use the same field. I construct the right-handed field from new left, and then I write a mass term, which is new left C bar, new left. This is of Majorana type. There is a more convenient way to write it, which is to write it as new left T, C dagger, new left. So, and I leave these to you as an exercise. Is trivial to do. You just have to take the dagger gamma 0 of new left C that I defined earlier in the lecture. But from here, you see immediately that this breaks lepton number. In fact, if I take new left and do e to the I alpha new left, a lepton number transformation, this term here doesn't contain a star, just a transpose. So this will pick up a 2i alpha, new left T, new left. So this is what is important. A Majorana mass term breaks lepton number by 2 units. So that is the first important thing to notice. Now, how do I diagonalize a Majorana mass matrix? Because this is what then will give me mixing. But first of all, we have to show that a Majorana mass matrix is symmetric. So M Majorana is symmetric. So, but it's also in the notes. But what we can do, let's look at new left T, C dagger, AmAm, new left. And I can take this is equal to its transpose, because it's just a number. And so now let's take the transpose of this. The moment I move this field on this side is anti-commute, so I will have a minus new left transpose, AmAm transpose, C dagger transpose, new left. And from the properties of the symmetrics, if you remember, C transpose is minus C. So I get exactly what I want, that AmAm is equal to its transpose, so it's symmetric. Now, when I have a symmetric matrix, its diagonalization requires only one mixing matrix. I can always write AmAm as a mixing matrix U, the diagonal part, and U transpose. This is the one which will enter into charge current interactions and from there in neutrino oscillations. So the idea is, we will deal with that this afternoon, that I try to come up with a nice form for this matrix here, and I will end up explaining at least this part of the PMNS matrix. As I will tell you later, there is also a component which comes in from the charge lepton sector. So really what you see in the charge current interactions is the product of the diagonalization in the neutrino sector and in the charge lepton sector. We will come to that later on. Now, when I diagonalize the fields like this, so I will have that my massive fields, I call them in the notes and left. This is gonna be, or in the notes to be precise, I put the dagger and transpose here and the dagger here. Okay, then these are my massive fields. And these are the original ones. And then I can rewrite my Lagrangian, let me do it here, in terms of a Majorana field, which I define as n left C. So I can rewrite the Lagrangian in terms of chi bar with the diagonal matrix chi, where this chi is n left plus n left C. So it's a Majorana field. So if I have a Majorana mass term, I can show that I will end up with Majorana fields. There's also the case in which I have both Majorana and Dirac mass terms. So what do you expect in this case? Do you expect Majorana neutrinos, Dirac neutrinos, or a combination of the two? You should know because Yoshi mentioned that yesterday. So you will end up with Majorana fields. The idea is that you are breaking lepton number, therefore you end up with Majorana fields. There is kind of, if you want, a special case, if the breaking of the lepton number is very small, so the Dirac term is very, very small compared to the Majorana one, then you have what is called pseudo-Dirac neutrinos, which is essentially two Majorana fields which have quasi-degenerate masses, but not exactly degenerate. So if they were exactly degenerate, you would have Dirac neutrinos. Here you still have two Majorana fields, but whatever effects depends on them will depend on the small difference in mass, which is the lepton number violating term. But you're still dealing with Majorana fields, though. Okay, so we can show at least, how much time do I have? Okay. 10 minutes. Okay, so you can show this formally, and actually you find it in the notes. I leave to you to look at the notes. There I propose an exercise in which you start with the Dirac plus Majorana terms, and you end up writing, finally, your mass, the Lagrangian term in this way, and you have a Majorana field chi, so that you can show this formally, even if we have looked at the physics. So what instead I want to do is look at the physics beyond the standard model. So how are we gonna explain now a Majorana mass term from extending the standard model? And let's start first with the minimal extension you can possibly do, which is, so we already discussed Dirac masses, so I'm going to focus now only on Majorana masses. So now let's look at the physics BSM. So masses BSM. So already said, we can introduce a right-handed neutrino and have a Dirac mass that in any case is an extension of the standard model because you're introducing a new particle and you are promoting what is an accidental symmetry to a fundamental symmetry. We have discussed already the cons of that approach, the pros and the cons. Now let's look instead at Majorana masses. So first of all, in the standard model, I cannot write down a Majorana mass term of this kind at the renormalizable level. This is because this breaks SU2. So this is not allowed to start with. You can arise only once you break the SU2 symmetry, and the best kind of I would say the simplest way to look at it is by the fact that if I go to the now effective field theory and I look at the first term I can add to the standard model, this is dimension 5, and this is exactly, well, I will have a coupling L.H divided by a scale lambda. So this I can do. This is dimension 5, preserves SU2. Once you break SU2 by getting the Higgs wave, then this will give you exactly the h squared divided by lambda, new left. So we'll give you the Majorana mass term that you are interested in. How can I generate, now, the question is how can I make this term appear in physics beyond the standard model? So, and here, what we want to do is expand this kind of point interaction. So think of it as I have the two neutrinos and the two Higgses. What I want to do is understand what is happening in this vertex. There are three ways in which you can open up this vertex. So this is new left, Higgs and Higgs. So the first thing I can do is I will have here my Higgs, the Higgs. So this is a new left and this is the Higgs. So this I can make the singlet combination between the two. So this will be an SU2 singlet. And in terms of Lorentz structure, you have spinor and scalar. So this will be a spinor. So this is what is called the seesaw time 1, and this is a singlet fermion. And this is called, well, right here, seesaw type 1. This is by far the most studied case because it's a very simple and natural extension of the standard model, which happens per se in many gut theories, etc. There are other two ways in which I can do that. But first of all, I can take, instead of making the singlet combination, I can make the triplet combination. And this is called the seesaw type 3. This is a fermionic triplet. And this is seesaw type 3. But I can also make, I have here new left, and here Higgs. What I need to exchange in between, first of all, is a scalar. And I already said that when I combine these two new lefts, I get a triplet. So this is a scalar triplet. Let me call it delta. And this is so-called seesaw type 2. So there are pros and cons that I'll mention in a minute. What instead I want to do is work out the seesaw type 1 case a little bit more in detail. because this is by far the most studied case. So in CISO type 1, as I already said, so you have a new fermionic state, new right, and is a fermionic singlet. So what I can do, I can write down in my Lagrangian, I will have a coupling L dot H and R, which respects the lepton symmetry. I charge both new left and right in this way. But it's a fermionic singlet, so there is no good reason why I cannot have a Majorana mass term for an R. So if I want to avoid this Majorana mass term to be there, well, it does nothing for the gauge symmetries because this is all singlet of the gauge symmetries. I have to impose lepton number. So if I want to avoid this term, I have to impose lepton number. If I don't, then this necessarily arises. And so what is the mass matrix? Once the Higgs get a wave, the mass matrix in the kind of new left and right C basis. So I have a 0 for new left. This is because of SU2. The EE term, kind of the low end, the active neutrino term is always 0. Then I have the Dirac masses here of diagonal, and then I have the Majorana mass in the and right term. So in order to find the values of the masses, I need to diagonalize this mass matrix, and assuming that MD is much smaller than MR, the two eigenvalues will be 1 and 2. I will have one which is basically MR. So the heavy particle doesn't really get affected, it remains very heavy. The other one instead, the mass is given by minus MD squared divided by MR. You can do this, just the diagonalization of a 2 by 2 matrix, in this case in just one generation. And so notice here what happens. If I take this to be GV squared, like the the tau mass, and I take here this to be 10 to the 10 GV, then I get exactly what I need in terms of neutrino masses. So I don't need to have very small Yukawa couplings. I can have Yukawa couplings as large as all the other charged fermions. The suppression of the mass comes from this very heavy new scale. And when I talk about 10 to the 10 or 10 to the 14 GV, comes to mind the problem of, the possibility of embedding this in gut theories. So I do not have time actually to discuss that in detail, but in the notes you find how to embed this framework in the context of gut theories. The first thing is if you look at left-right models, a left-right model has a kind of this symmetry between the left and the right sector. So you have new left, you have to introduce a new right. Once I introduce a new right, this is unavoidable unless I do something to avoid this. I impose some symmetry to avoid this mass term. It's not the case. It arises by the way I look at by the Higgs sector, which breaks the left-right symmetry. And even more so, I can embed this in a gut theory of the kind of SO10. SO10 also requires a right-handed neutrino in the fermionic representation. And again, by the breaking of SO10, I can generate a mass for the right-handed neutrinos, and so induce a CISO very naturally. So that's why this CISO type 1 model has emerged as a very favored type of mechanism from a theoretical perspective. The other two CISOs have pros and cons. The problem is that I'm dealing with triplets, either scalar or fermionic triplets, which means that they cannot have a very heavy mass because I need to preserve SU2 down to the electroweak scale. So these need to be relatively light, and so the question arises, why do they have masses which are quite light? But also means that if they are quite light, if they are in the TeV scale region, maybe you can produce them at LHC, maybe you can test then the mechanism. So there are pros and cons, and so people have, especially in recent years, there's been quite a lot of work in these type of models because they allow a direct testability at colliders. So there's a lot more information in the slides, but I think it's time to go for lunch.